Okay, so there's a lot of talk and buzz around AI or artificial intelligence. Some people use the terms data science or machine learning as well. But what really is AI? At least in like like in a general sense. Um, so in the next slide, we see that people think that AI are these complex, intelligent beings, and eventually will take over the world. So like in Terminator, which was a while back, but then like in recent like pop culture, this is kind of what people see AI being. But and either that or just like it's overhyped. Like AI can solve um like many of our problems, but it's not that simple. If you think about what we can do with AI today, um, AI is actually just really, really good at really, really good at doing very specific tasks. And although there are some people who are working on more intelligent systems and with a goal of having artificial intelligence that is as smart as people, we're really quite far from that. I, like Div and I don't think that we'll reach this state in our lifetimes. So, what's an example of something that AI today can accomplish? So, one specific task that artificial intelligence is good at is called object recognition, or computer vision. This is identifying objects in a given image. So one really famous example, as illustrated in this slide, is the dog versus cat problem. So the AI or the machine learning algorithm, in this case, what is called a neural network. A neural network is usually used in object recognition problems. So the AI sees thousands and thousands of images of dogs and cats, where each image is labeled dog in quote, like dog, as kind of like in this slide, or cat, and the network then learns to differentiate between the two animals. It's not really how we as humans learn to distinguish dogs from cats. It's a different sort of process. We don't need like thousands and thousands of images or examples of dogs and cats to distinguish the two. It just processes information in a different way, and Divya will kind of talk about that more in detail later on in the presentation. So let's connect AI to healthcare, and bring up some history behind that. So in the 60s, people have been trying to explore what artificial intelligence could look like, and some folks tried to recreate a doctor, um, or a diagnostic system that used a form of AI called natural language processing, and it was useless. It was pretty useless. It was way too general, and you can see why if you read through the conversation of a patient with this doctor, which they named Eliza. So it goes, "I've not been feeling well. Don't you ever say hello? Okay, hello. How are you today? What would you like to discuss? I'm not feeling well. How long have you not been feeling well? Since yesterday. What does that suggest?" Yeah, so like it goes on, and it goes on in circles, and nothing gets resolved. Um, and then after the 60s, for a couple decades, there's this kind of gap in in the whole kind of industry. People talked about it less, and there's this like AI winter. And then recently again, it's been coming up and becoming more prominent and popular and hyped. So over the last decade, we've seen a resurgence of AI, and AI in healthcare. So now some popular areas are, I mean, this was brought about by um, people, again, like publishing papers in the space and things like that. And some popular areas are now in diagnostics, in patient triage, in drug discovery, in precision medicine. So here are just some snippets of news articles from the last couple of years or so of some startups or researchers who are, who are discovering things or making use of AI in various applications. And some famous players include Google. So this subsidiary of Google called Google DeepMind, which is heavy on research. IBM Watson, Siemens, Microsoft, Hanover, many startups, a few government agencies and research organizations. But of course, there's a caveat. There's AI is quite hyped, some overhyped sometimes, and it does have its limitations. Because this was a case study, or this was something that happened just last year, where IBM Watson wanted to recreate its own sort of ELISA, or like a doctor, or a tool that diagnosed way too many too fast and in a way too general manner. So because it's so good at, and they in effect failed on their promise to deliver that. So because it's so good at specific tasks and not yet generalizable enough, so programs that attempt to solve too many problems, such as IBM Watson in this case, are failing. The initial goal was to build an all-knowing AI doctor that could diagnose a wide array of health issues, when AI, as it stands, is much more effective at tackling specific tasks or specific problems. And that's kind of what we are aware of now, so that we take kind of this piece of information as we work on the project or projects in with your hospital. So I'll pass this on to Div to kind of go into a deeper dive into AI for cancer detection.
Now we have better AI systems that work for very specific tasks. And that means for us to be really successful at what we're trying to do, we have to be very clear about our goal as to what we're trying to define, what we're trying to train the model to do. And we can do it in multiple number of ways. So I'll walk through some examples of how we can formulate the particular. So even the task of saying, let's detect cancer from slide images is a very big generalized task. So that's why we started our first case with breast cancer, metastasis in the lymph nodes, and even that could be formulated in ways that are actually not specifically good for us, or could be better formulated. So before I go into the specific ways we could actually formulate our problem, I'll walk through the two most common ways people do cancer detection today, the most popular approaches. The first, they're both kind of what we call supervised learning. And this means you are training a model. The model is basically a mathematical, it's just a bunch of equations that you're getting the system to learn something from it by giving it examples. That's why we call it supervised, which means you have examples of what a slide, if it has cancer or not. You tell the system that, hey, this is an example of a cancerous slide. Hey, this is an example of a dog. This is an example of cat, and so on. And then you also have other kinds of machine learning techniques that are unsupervised. In those cases, you don't actually tell it what to look for. You don't give it labels. You don't give it any kind of information on what it's supposed to learn. So that might be an example of learning to translate between two different languages without telling what translates to what in those languages. Suppose you had Hindi and you had English, and you know that you've basically trained a generalized network that would learn how people speak generally in Hindi and in English, and then it just learns to kind of figure out, hey, whenever people say certain things in English, it appears with certain words, the same way you have patterns like that in Hindi, and then it just picks up certain commonalities that are just generic and true for language. So ideally, we would have this kind of a learning done for cancer detection as well. Problem is, these kinds of techniques for unsupervised learning are not good enough for us to get there today. There is no guarantee that we will get somewhere that is meaningful, that we can actually confidently believe will actually work. That's why we prefer to go the route, and most people do often go the route of supervised learning, because when you do supervised learning, you're giving it clear examples of saying, hey, look at this and learn what I'm showing you. If I show A 100 times, can you learn to find out A the 101st time? And so the first portion of this is you can formulate the cancer problem that we are looking at as a classification problem. By classification, we mean we're teaching the system to learn to differentiate between two things. One is you're saying, hey, look at the slide and say, is this cancer? Is it not cancer? One class is not cancer, one class is cancer. And if you give an image, it's just trying to do one thing. Just trying to fit that image and say, does it have a dog? Does it have a cat? Is it cancer? Is it not cancer? So any problem that you want to define, which has clear, just one thing to learn, and you're just trying to figure out which class it belongs to, that's classification. The second kind of problem is called segmentation. And here, what we're trying to say is, if you have an image or a cancer slide, you want the system to be able to detect where is cancer in the slide. So you want to be able to segment the image, the portions of the image that are normal or abnormal. So that is also a kind of classification, but you're getting more information from that system. So it's a harder problem to solve. So I'll quickly walk through an example of what that looks like. Sorry. So this is a classification problem where you're saying you look at this sample and you say, is it normal or abnormal? Is it normal or abnormal? But a segmentation problem is going to look at being able to say, draw this green line and say what is inside it is all normal cells. And what is all inside the red ones are all abnormal cells. So in a sense, what it looks like would be something like this. So the system learns to figure out what are the red regions. So you said in this image, in your training example, you said these portions are red, whatever red means. Red could mean it is cancerous or it is normal. In this case, it specifically means certain kinds of medical terminology that I'm not aware of. But you're basically saying this is one kind, all the reds they look like this, find out where the reds are. And your system learns to figure out every pixel in the image and say, this is a red pixel, this is a yellow pixel, this is a blue pixel, and so on. So this is how in cancer, in our particular workflow, this would basically be cancerous regions, non-cancerous regions. And obviously this is a better way to solve our problem, because in this situation, all the lab technicians will have to do is look at the region and be like, does this look right to me? As opposed to them going and how they're solving it today, which is like finding out and looking at it and analyzing what is the radius of this thing, what is the density of this thing, and so on. So for our first proof of concepts, we would ideally go with a classification setting that is just looking at the whole image and then asking, is there cancer in this or not? And the second approach, the better approach, eventually the ideal one that we want to get to is segmentation. And this is our understanding of the problem today. Okay, so how does the system do this? It does it by first, all the system is looking at is a picture. The slide images that you have after you've done the staining and you get the results of the staining, it's basically just an image. So it's a JPEG or a PNG image, which is in the system represented as a bunch of numbers. So in this example, this is a 28 by 28 dimension image. So it's just a PNG with 28 pixels in each dimension. And if you can see here, it's basically just showing the number 8. And what the system really looks at is not this image the way we see it. What it looks at is basically all the black pixels are 0. The whiter the pixel is, the closer to white you are, the number gets higher and higher. So the maximum number your pixel value can be is a 255. Like in color gradients, you might have heard of how colors are represented in as compositions of three different colors: red, blue, and green. Or if it's black and white, it's just contrast from like black to white, which is 0 to 255. So all the white pixels in the 8, if you can note, are you able to see the picture? Well, you can see some numbers here, right? It's 242, 208, 111. So basically, wherever your image or your numbers 8 were, or the pixels for 8 represented the white pixels, they have higher values, and everything else is black. So the system behind the scenes is really just looking at this. It's like a matrix. It's a matrix of 2 dimensions where you have a bunch of zeros and then some non-zero elements. So if a system was trained to learn, is there non-black pixels in my image, then all it will have to look for is there any value in this matrix that didn't have 0? And that's a simple enough test, right? Your system is just learning, is there a non-zero value in this matrix? If yes, say yes. If no, say no. So what we essentially want to do, for example, then is, when we want to classify, in our case, cancer and non-cancer, is it's going to try to learn patterns in what these images look like. So if you have higher density cells in cancerous, I may be wrong in my examples or analogies, but please bear with me. So if you have higher density cells in your cancerous slides and lower density cells in your non-cancerous slides, these numbers, the patterns will look very different, right? More dense, the more dense it is, these numbers will be like in bigger numbers or in similar clusters. So these numbers will not be so far apart. They'll be like lots of closely related high numbers, and then some areas with blacks or whatever. And then if it's a normal image, that density will not be as high. And those are the patterns the system is looking for. So it's not that it's going to measure what is the curvature of this curve here, what is the edge here. Those are not the things the system is learning. It's really just picking up patterns from the numbers. I walked through this very quickly earlier, but I'm going to do it again properly because this kind of is the core part of our presentation. So this is an example of the classification problem, the first level that we will attack. In this case, the whole slide, this is the whole slide, right? And if we present different patches of this slide, so let's say I divide the slide, the image into a grid of, let's say, 3 by 3 or something like that, and this region and this region and this region are all different samples, then, and we give the system information about whether there is cancer in that particular patch. So because of the annotations here, the green regions are the non-cancerous portions, the red regions are the cancerous portions, right? So if my patch only contained this green region, then what I will tell the system is, hey, this is an example of a sample that is actually normal. Then if I give a patch that looks like this with the red portion in it, and then I'll tell the system, hey, this is an example of a cancerous portion, right? So what this will allow us to do is, if you take a whole image, you're basically training the system to look at the finer details. When you look at, when these are represented as numbers and there's more resolution, right? We don't see the finer details of what this looks like, but the system will be able to capture more of this because we have in the image slides that you give us more resolution. So if I remember correctly, when I mentioned it to Abhijit that we wanted examples of sample slides from you guys, and he was like, which level do you want? What is the resolution you want? So it's the same thing. So if you have the highest one, looks like it looks like there's not a lot of information between the two of them, but if you go deeper and deeper into more resolution, you'll be able to find, this is what I guess you guys do as well. So the normal one looks like this, and the tumor one looks like this. For example, if you look at this particular example, the normal ones, there are lots of darker, denser regions, and so the numbers and the patterns here will be higher to lower, closer to 0. And then here, there's like less dark value. So you'll be somewhere in the middle, and like a lot of whites, which are like going to be closer to 255. And so then the distribution of the numbers in this and this one are going to be very different. And that distribution is what, over many, many examples, it's going to like learn a pattern over that. It's going to generalize a pattern over that distribution. We're like, hey, my normal images always tend to be darker, tend to be denser. But what does not happen is the system does not automatically know what is darker, what is denser, what is actually happening here. It doesn't understand any of that. All it looks at is, like in this previous example, a bunch of numbers, and it's just saying, hey, whenever I see big numbers like this in this pattern, I'm going to say X, which is cancer or not cancer. That's it. It doesn't know what is the shape, what makes an 8 an 8, what makes a cancerous image a cancerous image. We don't know if it learns. Unfortunately, that's the state of the systems right now. How do we actually go from an image that is a matrix of numbers to the final detection? What is actually machine learning? What are we essentially doing? So in the example of the classification scenario, we have a patch, which is a portion of the original slide image with the label that says, is this tumor or not tumor? So you basically give it an example and you have an answer. It's basically you're saying, I have a question, is this cancer? And you have an answer, but you don't tell the network the answer. What you have is a bunch of neurons, what you call neurons, which is nothing but, it's the same. It's basically, if this is 81 cross 81 pixels, you have 10 versions of that here. And you're basically doing mathematical operations called convolutions. If you guys have taken signal processing or know about Fourier transforms, this is nothing but Fourier transforms. So the convolutions of signals that you might have done in your high school or university is exactly the same as this one. It's nothing but a mathematical operation that you do on a signal. So in this case, we are saying, take this image, take the values of this guy, and then just multiply it by something or divide it by something, and then it comes up with something else. So for example, I'll just show you what a convolution operation can do. Okay. So as we went through before, an image is basically just a bunch of numbers. So in this image, every pixel is a number. There are some 200 something numbers here. Closer to this guy, it's like 20. So lower the number, more black it is. And so a convolution operation is basically doing something like this. You take an image, you multiply the pixels by some numbers that are given by what you call a kernel. And then at the end of it, you could have an image that is basically exaggerating or picking out patterns from this image that you want. So in this particular case, you said sharpen. It basically sharpened everything. The darker, blacker pixels became more and more black. The whiter pixels became more and more white, which is what you would do if you increase contrast in your TV, or if you use an Instagram filter. It's exactly doing this. If you have an Instagram filter that added colors, it's doing nothing but a convolution operation. So let's go and do maybe blur, right? So if you see here, it now blurred your whole image, right? So if you do multiple such operations, you're going to extract more and more information from your image. So essentially, in face recognition or other image tasks, people used to before find a corner, find curvatures, or find patterns that look like a face. So it has two eyes and a nose and whatnot. Find a pattern like that. You can basically define such things and look for them. What machine learning is allowing us to do is you don't have to find out what your pattern is supposed to look like and then define those operations. Instead, it learns these operations by itself. So when we are learning a method, or like a network is trained to learn something, it's basically learning the values of these convolution operations. So this is a kernel that is learning how to blur, sharpen has a different values, and so on. So it's basically creating a kernel like this for different things that in combination will give you an answer for your question, which is in our case, if I can resume the presentation, is it tumor or not? So basically you have a bunch of, like what we just saw, convolution operations, and every one of these is a different operation. So one could be blur, one could be find out edges, one could be find out, sharpen the image, one could be some other kind of filter. And the results of that are then combined and another convolution operation is applied. And this keeps happening a multiple number of times. And we don't define what these are. All we tell the system is, hey, here's an example, here's an output, this is what I want you to learn. I want you to associate this example with tumor. And every time you see a tumor, you're going to then adjust what's going to happen. So if it makes a mistake, we learn through that mistake by saying, hey, why did you think this was actually not a tumor or a tumor? If it made a mistake, you'll be like, you made a mistake. Now go and correct the values here. Go and correct the values here. Go and correct the values here, and so on. So that's why it's very important in machine learning tasks to give it a lot of examples. If you give it just 10 examples, it doesn't have enough to learn the correct values for all of these operations. So let's say I need 5 values for every single operation, then you can multiply all of this and it'll be like a million things you need to learn. And you can't arrive at the correct optimal values for them. But if you have 10,000 examples, then you have more situations where it's going to fine tune what it's learning. The first 10 times it's going to make mistakes, 15th time it's going to make mistakes, 100 times it's going to be like, I think I know what's happening. And then by 10,000, it's like it's learned it so well that all of these values are like probably the best it can possibly be. That is why it's really good at learning one task. If you ask it to detect lung cancer and breast cancer and all these other things at the same time, these values will not be the same, right? Because the image visually for dogs and cats are very different. If you put dogs, cats, zebras, everything into one, all it can learn is this is an animal. And maybe if you put it against sofas and cars, it'll work fine. But within the animals, it wouldn't know what it's looking for. But if you train it specifically to just detect dogs, no matter where you are, it'll always pick out dogs correctly, but that's all it can do. It's very good at that specific task. So far, so good. I can walk through the example of the ideal situation as well, but if it's too much, we don't have to do that. So the ideal scenario is, in the previous example, we said, this is a portion where there was cancer, and all you had to do is, for different regions, say, is there cancer here or not? And the system is just learning to say yes or no. So it's like asking a question, is there a dog in this image? Yes. Is there a cat in this image? Yes. In the ideal situation, you want the system to say, is there a cat in this image? Yes. Where is the cat in this image? And it should be able to tell you, look here, the cat is here. So that's exactly what we're trying to say here. So in this example, the left side, this is an example of a pathologist who has annotated the slide. And in this side, it's a system that has been trained to exactly mimic what the pathologist has marked as important, as a category. So it's still doing classification between the 4, in this case, 3 categories, four categories, yellow, green, blue, and red. For my convenience, I'm going to just say that. You may know what these are. I don't. I'm so sorry. So in this case, the pathologist has, for the first slide example, marked this region as red and this region as yellow. Now, the system is not just saying, is there yellow in this region? Is there red in this region? It's trying to say exactly where. If the pathologist marked this area as yellow, we want it to ideally mark every single thing as yellow and the red as the red. And the other ones are not marked, and we should ideally not be saying anything there. But if you notice, there is a small portion here that is slightly yellow. So this is a harder problem, obviously, right? Because it's not just trying to figure out a yes or no. It's not just saying, it's not as simple as saying, is it a dog or cat? It's actually trying to say, there is a dog. My dog is most likely in the left corner of this image, and everything else in this image is less likely to be a dog. So for it has to learn more nuances of what it looks like. It's not just the pattern. You have to extract information like, where are the edges? Where are the curves? What kind of behavior should I look for? Ultimately, it probably learns the same things that humans look out for in these things, but we don't yet know, or we don't have studies that show that it is the same, unfortunately, because we don't have methods that look into the convolution layers like what I talked about earlier to see what they mean. We don't really know exactly what it learns. That's why most AI systems are black boxes. So this is an ideal case. The problem with this particular thing is we need labels for every single pixel. So our annotation is basically this. Someone has drawn a very neat line across all of this, right? It's painstaking work. And then we need to convert every single pixel in this image into 4 categories. Is it red? Is it yellow? Is it blue? Is it green? And the fifth one is no label at all. And I guess in the sixth, this is the sixth one, which is dark black or whatever. So it's trying to distinguish between 6 things. And instead of saying this region has something, it's trying to say this pixel is of class A. This pixel is of class B. And in this case, your system is also going to be very sensitive to your resolution. You can't just zoom in or zoom out and expect the system to learn the same thing. Because obviously, if you train it with this kind of resolution, it's going to learn something different because your pixel looks different. If you're zooming into a different layer and it looks like this and you train the system, it's going to learn something completely different, right? They look visually very different, and their matrix values for what they are represented in terms of color is also going to be very different. And so if you train a system on this, you cannot expect it to work well on this one. And so all of those sensitivities have become more exaggerated in this case because you're actually doing, if this is a 1800 pixel image, you're making 1800 predictions, and that's 1800 as many chances for us to go wrong. It's not as like if you make a mistake in 1 pixel, it's okay, but imagine the domino kind of effect it could create. The system could be like, oh, this is a cancerous, this looks like it might be a cancerous place because it's dense or whatever, and then it's like no, the next one is non-cancer, so this is most likely not cancer, and so on. So it's the what I'm trying to say is the errors will be compounded because it's got one more level of complication added to it. And it's also going to take a lot more to train this model because you're trying to learn more information, which means the number of layers that we learned last time, this is just to learn to answer one or yes or no, right? Just 2 things it's trying to learn. If you want to learn resolutions of this scale, you usually need orders of magnitude higher in terms of the layers, which means the number of actual values you're trying to learn of those kernels that I showed you is going to be higher, which means more time taken to train, more examples needed, more importantly, to train that. Okay.
It would be more amount of resources, right? Computing, storage, electricity, all of that, right?
Exactly. But so the good part is once you train something like this, you can actually transfer learn, which means if you have a problem that it does really well. So what people have noticed is if you train a system with a very well curated data set of like 1000 objects, they have learned that you can take that any model trained really well on those data sets, which is distinguishing between 1000 categories. So it has like cars, everyday objects, animals, whatever. And then you take that model and apply it to a problem, like in the case of, in our case, even cancer detection, you can still take some of those learnings with you. So you can transfer that. It's kind of like saying, I learned really hard maths, but to do that, I learned multiplication tables, and I learned to do differentiation and integrals, and I learned to do something more complicated, and so on and so on. But then if I want to do some other task that is also math, but not the same, I can still reuse some of the earlier things I learned. The fundamentals that I learned still exist. In this case, the fundamentals will be those early layers, which are learning things like, are there edges here? Is there a white spot here? Is this a generally bright image or a dull image? Things like that you can still transfer between domains. So if you have cancer detection done really well on one data set, let's say for lungs, you could potentially transfer that to other similar kinds of cancer problems, and you could see good results with lesser number of examples. But you will, for the first task, you still need orders of magnitude higher examples. Okay. The workflow for the learning, in this case, you have a sample and you want to say which regions are what. It is still the same, but like the layers are still the same. You'll just have more number of them or different kinds of operations here. So the complexity of those operations may be slightly different. But in the end, your prediction is not just saying predict 2 things. It's trying to say one prediction for every single value. So if this is a 1800 image, number of pixels in this image, you will make 1800 predictions for this one. And then for every single mistake you make in the pixels of this image, you will go back and correct the values of all of the kernels that you're learning along the way. So this is a harder problem to get very high accuracy on. But people are doing this. It's getting better. So I'm confident in the next 5 to 10 years, this will be like the easiest thing to do for cancer. Like we're in the stage where advancements are happening really fast in this domain. Okay. So to summarize, we talked about the two different ways we could potentially go forward with our use case. Obviously, one is simpler, one that we recommend, one is ideal, something that we want to work towards. So if we build a data set, we ideally want to build something that is going to help us in the case of the ideal one as well. So we don't like, if we're taking time from the doctors, if we're taking time from the technicians, we don't want to like take too much time again and again to collect those data sets. But to summarize, any kind of machine learning system that we use today, especially if it's a deep learning network, which is typically the case for any kind of problem that uses images, because they have the best performance. They are black box. As I mentioned, we know it learns something. We can sometimes even see what it learns, but we cannot actually go into the finer details and identify what led it to come to this conclusion. So if there is an image or a slide and it said this has cancer and it doesn't, we cannot with any way confidently say why it came to that conclusion. So if it's a human and they said, I think there's cancer in this thing, they'll be able to tell you, because I saw this, this, and this, and usually when this, and this happens, there's cancer. We cannot see that from such a system. The second thing is the amount of examples we give it, the quality of those examples, and the diversity in those examples matter a lot. So if you only show chihuahuas to the system and say these are dogs, and then when you're actually putting it in production in real life and you show it a Labrador or some other kind of dog that doesn't look like chihuahuas, it's not going to be able to predict that at all. So if you want to learn to detect all kinds of dogs, even though dog is a very specific problem, your data set should be representative of what you will see in real life. So if you can say, like majority of the cases are, you yourself will know, not all cancer cases look the same, right? They will have variations of different kinds. So you should be able to identify those things in all or represent them in your data set as well. So your data set ideally has chihuahuas, Labradors, and whatever other kinds of examples or typical examples of cancer that you want to be able to predict in real life. Not saying that it's able to predict chihuahuas, but I'm saying even to detect if there is a dog, you need to have the representation because it has to have seen it to make some kind of conclusion about it. And as we mentioned, it is task-based. So if we have, let's say, x-rays, mammograms, cancer slides, FNA slides, all of these will be different tasks. And all of these will be different models for different locations in the body or different types of cells. So if it's a lung cancer cell that we want to detect and it looks different in different parts of your body, then they probably will be different tasks. I don't know enough to say if they might be the same task if no matter where lung cancer is in your body, but it really depends on the particular task. But it is task-based. We cannot build one model that is able to say all kinds of cancer, I know what to do with it. It's exactly what happened with Watson. And we see many, many such examples in the market today where startups and everyone is trying to reach for the skies, and it's overhyped. You cannot get there, and it's not recommended to get there because we really are playing with people's lives, and we want to be able to give them our best solutions. And if that is the case, we really want to be able to tell the system to be good at what it's really good at. It's really good at doing very specific things. We should capitalize on that, and everything around it we can engineer. So we can have 10 models, each of them predicting different kinds of cancer, and give an output for every single thing. And then you can be like, hey, you don't have lung cancer, you don't have breast cancer, you don't have this cancer, and so on. But getting it to work in one shot for all kinds of things we want answers for, we won't be able to do. And another thing that I remembered from one of our earlier conversations was the doctor mentioned something about being able to help the radiologists by giving things like diameters of the cells, or certain properties that the cells have and how you measure them. So I would see each of them as a separate task. So if you wanted to predict what is the average cell distance, or what is the cell wall or cell lining thickness, and things like that that you normally measure, all of those will be specific tasks by themselves. And in those cases, let's say you're trying to predict the width of your cell lining or your cell wall, that will not be a classification task, because you're not asking in the question of, does it belong to category and then 5 categories, right? It's going to be a number. So it's a variable continuous number. So it's 5, 6 centimeters, or 1 millimeter, or nanometer, or something like that, right? So that's a different kind of problem. There are still lots of solutions for that too, but it's a different kind of problem, and they will all be separate tasks. So if we can definitely, of course, build systems like that, but each of them will need a particular kind of data set that teaches the model to do exactly what we want it to do. And the more tasks, so the more complexity we add into our pipeline, as we saw, we will have compounding errors, because making one mistake, let's say we say our system is 75% accurate about something, then if you make one prediction or 1,000 predictions, the percentage is 75, right? So it will the number of errors that you like, the more you ask the system to make predictions, it's going to make more and more mistakes, and on average you'll have 75%, but then you will start to see more and more examples of where it's not working. I don't know how better to explain it, but yeah, you guys probably already get it. Okay, that is the end of the second section, which is about how we are looking at it. The last section is how we're looking at the infrastructure and the data sets and stuff, but we can stop and take any questions if you have any.
Okay, so I have a question. So in terms of looking at the various AI algorithms or neural networks, so in terms of our plan, is it something that we leverage upon existing algorithms or AI services, build on those? Because you mentioned this field is rapidly growing on a daily basis. Or is it something that since this is task specific, we have to do it like from scratch, that is from the ground up?
So let me clarify that a little bit. Yes and no. So we won't have to, okay, there's two portions to this. One is, if you go back, this is an example of the network layers, right? Okay, this is a better example. So we have, let's say, the architecture for the network itself, for us to learn a good model, like this portion, this entire thing, like the ordering of these operations, the choice of different ways to actually train the model itself. So when you make a mistake, I said something in passing about how you will correct, you'll pass that mistake and how off you were in your prediction, and like transfer that or like propagate that particular message down the stream to correct the values here. There are lots of choices in the methods for them. So those are some things that we will be definitely taking, and we will not be inventing those things. It will be just best practices, the best performing architectures, best performing models for this particular task, which is cancer detection. What will not be directly applicable for us is existing services that are like offered by Google or AWS or all the big companies, because they typically tend to be for plug and play use cases. So if you are looking for face recognition very specifically, it's now considered a solved problem, and you can just be like, okay, my data set for faces looks like this. Can you identify all of these people? That's a smaller problem to adapt to. And so you'll be able to leverage the APIs that they have. So you technically won't have to build anything. You don't even have to train much, and so on. But for this kind of problems, um, like especially like the ones that we are doing right now, I don't believe we have APIs or tools from companies that we can directly just apply. They It's more for people who want to be able to quickly build it. It's more like a toolbox plug and play kind of thing, as opposed to being able to really get to the best. In our case, for this, like the architecture portions, we are using and reading and taking from the papers. Like the example that we mentioned a couple of weeks ago, our performance was like around 80 something percent on the data set that we sent along. That was like we basically did not a lot of work in figuring this out. We just picked it from a paper. Whatever they mentioned, we did those things. The pre-processing, whatever they said, we did it. And then we're going to work on top of it, but we're not going to be inventing the wheel in that side. But we will be making our own implementation. It will not be from. Does that answer your question?
Yes, it does. So essentially, apart from the known tech vendors, whether it's a Microsoft or an AWS, I was also referring to in terms of the ongoing research by, of course, the clusters in Canada and the North American region, because I keep seeing a lot of these hospitals and doctors also creating these various algorithms,
Yes.
open source stuff which is happening. So I was referring more to them than
Those
the actual infrastructure services.
Perfect. So those are in the realm of the architecture here, like what I mentioned, and those are absolutely, we're not going to reinvent them. We're going to take exactly what they're doing. The only thing that I will bring attention to, I guess, is the focus in the West and in most research now assumes that you have the best data set, assumes you have the best high quality, high resolution images. Usually the data sets are curated by well-funded hospitals. They have a lot of manpower and money to throw at it because they're well-funded. So what they're really trying to get at is the best accuracy for detecting cancer or doing more fancy things with it. In our case, our bottleneck is not to get to that, more so to be able to operationalize it so that it actually can be applied in real life. Even in Canada, I see a lot of work being done in the research space, but I don't see it yet being operationalized as much, which means there is a big gap between research and being able to successfully launch it and have it be useful and workable in real life conditions, especially that given that it's going to be in with patients. You will have obviously to go through a lot more testing, a lot more a lot more work to say this is ready to be deployed. So that is still the biggest gap. And in our case specifically, we don't have the kinds of things that work very well for, even the methods that work very well for the researchers might not work for us, because we probably wouldn't have the same resolution of images, the same quality all the time. And that's not to say that we cannot get them, but that's not useful, right? We should be able to replicate that thing day in, day out in the hospital. So our training set should be as close as possible to the operating conditions in the hospital. That's when we'll have a good operationalizable model. So we will definitely try our best to adapt and see what existing research can help us to do. But our focus and our problems are slightly different. And so we will have to very quickly adapt to making sure that it is operationalizable in the end. So the doctors cannot work with it if the end results are not reliable enough, if they don't work with the systems or the kind of conditions that the slides are taken in during production time, then those are the things we have to focus on getting right.
When we have to provide data sets, we will scan the slides, and then on the slides we have to mark out these areas, right, where there is cancer where there is no
Or
cancer.
the ideal case. Yes.
So we have to do breast cancer separately, we have to do lung cancer separately, we have to do stomach cancer separately.
Yes.
So if we are just looking at lymph nodes, for example,
Yeah.
that's what we should be doing.
Yes. And ideal. That is the ideal case.
Mhm.
But to start with, we can do. So that was a thing I was gonna go into next. So to start with, we can start with something as simple as just
We
labeling.
don't have to do we don't have to do segmentation. We just have to give you the slides and say
Yeah.
normal slide, abnormal slide.
Exactly. We can start with that, and then of course we'll run into problems with like the way we're transferring the data, the way we are storing the data, the operational stuff, and the infrastructure stuff. So we can like get those out of the way because it'll take a few iterations for us to get that right. Once we get there, then we can spend a bulk of the time in getting to an example of an ideal set, and then we can see how it works. Because ideally, we don't want to be spending all this time and creating the perfect data set for every single thing and then finally have nothing work. We would rather do it in smaller cycles that are like iteratable and then slowly build towards at least one example of an ideal one that then we can compare and say, hey, does this work for our particular case? And can we show that it works consistently in a reliable way?
Do you think it will be easier to work on X-ray images to start with?
Um, can you walk me through why that might be a different?
Because for pathology, each slide has to be seen, scanned on a computer, and then marked, and then there will be in a slide there will be many areas which are abnormal,
Mm-hmm.
and for one or two pathologists to annotate every slide
Mm-hmm.
will be a time consuming job, will be a sort of full-time job.
Even for the classification case where you just have to say it's
Classification will not take time. We just abnormal normal is like routine, no?
okay.
We can scan all the abnormals, scan all the normals.
Okay, got it.
Whereas in an X-ray, every doctor can contribute.
Okay.
So for us to mark out the abnormal areas on an X-ray would be a faster learning process and faster execution process.
Okay. And in the X-rays, do you also have like cancerous regions and non-cancerous regions?
Yes, we have abnormal. Everything on X-ray will not be cancer. Ultimately, for cancer, we have to come back to pathology.
Okay.
But we can start pointing out normal X-rays and abnormal X-rays, and we can actually annotate what is abnormal in the X-ray.
Okay.
We can look at both. I'm not against the idea of looking at pathology. I'm just looking at the amount of physical labor that will go into it and whether
Makes sense.
that will become a bottleneck.
Makes
I think the 2 points maybe clarify more to doctor is one is how many sets of data that you would
Yeah,
require,
yeah.
right?
yeah, I
The
think that.
second, yeah, the second aspect is also in one of our earlier calls, you had mentioned that you already have a training data set for the pathology, not for X-rays, right? So it's more about what's the testing you want to do. So if those are the two facts which is there, I think maybe if you explain to him, then maybe we could decide one way or the other.
So
I have something more also to add. So, from what I understand, we will need more the number of slides, more the number of data sets, more will be the accuracy. So if we say 10, 100,000, 10,000, 10,000 will probably give us the best results. A. B, in pathology, I'm also looking at quickly converting this into, or relatively quickly converting this into something that we can actually test in the clinic. And for pathology, we have to train for lymph nodes, we have to train for, you understand the number of cancers, the number of patterns of lymph node metastasis, the number of patterns of response of a lymph node, even something just as simple as a lymph node metastasis will have, my opinion is 200 different variations or even more. And if we have to train the system, we will do that. We have to do that, But if we can put in some basic thing from the pathologist point of view, it will be a lot of work. From your side, I don't know how much of hours you will put in, but I think it may be good to have somebody who will do this job for 3-4 hours in a day. And for a practicing pathologist to get out that kind of time on a regular basis, maybe a challenge. Radiology, the advantage is for us to recognize abnormal radiographs, the workforce available to categorize X-rays is much larger, and the time taken to categorize abnormals is much less. And the specialization required to train a doctor to identify something abnormal is also much less. It may be from the input point of view, it may be easier to provide data sets for X-rays, less time consuming, and for the time spent, more output in terms of number of data sets than for pathology, I feel. I'm not against either idea.
Okay, those are very good points. And Mr. Chandra brought up something that we completely forgot to bring up. So regarding the particular point of X-rays versus slides, the one thing that we did not connect back to what we did today is the model that we trained a few weeks ago was from this data set. So this data set has 100 normal, 70 metastasis for lymph node examples, and this data set has like 40 levels of magnification, annotations made at the pixel level, right, to detect breast cancer in lymph nodes. So what we did was to be able to train a model on this data set, and then we showed a test performance of 80% on this data set. The good thing by using this kind of a existing data set is we don't have to create those 10,000 examples for this particular case, right? Because it's given to us for free, and granted this particular data set is really high resolution, idealistic conditions. But what we want to be able to do is from the examples that you guys give us and the data set that we collect from you, which will not have to be in the order of tens of thousands, but in hundreds, because we already have learned, like I mentioned about the transfer learning. So when you know how to do really well in this idealistic conditions, and you train with a little bit fewer examples from your side about realistic conditions, we can build a model that works really well for our case without having to create those 1 million examples. Like in this particular data set, they have 1 million patches. So highest chance of success in my mind is using this, because even if we go the route of annotating specifically from the side of X-rays, we will not get this kind of a well-made data. I'm not saying we will not. We can find some other data sets that have similar things, but this is a better starting ground because this is a competition. The paper that we found was on this competition, one of the best ones that had the best results. So like someone had worked like 1-2 years to figure out how to make it work for this guy. We got it for free, right? So those might be the things we'll have to figure out which starting point could get us to the next step faster. It may not be available in the same way for all kinds of tasks we may take on. So for example, stomach cancer or some other kinds of cancer which are not as commonly studied in this field, we may be at a loss for how to start. We can still learn from what we learn from these kinds of problems, but they may have different challenges that we don't know of yet. So that's point number one. So in this particular case for lymph nodes, not generally for all kinds of slides. So I agree with your point about, yes, the doctors can, the human hours in collecting the data set and the resources is very important. And that's one of those operational challenges, right? We don't want to create an additional burden of like taking away the most important task from doctors' times and lab technicians or pathologists' times. So in most cases that works. But for the particular case of lymph node with breast cancer, which I still recommend to be our first choice, this already works. We have a good performing model. We should be able to take very few samples from and be able to adapt to that and test it in real life. And we don't have to do segmentation. We can do classification. There's going to be a lot of operational challenges that come up. Let's tackle them. In the meantime, we can look at data sets that have x-rays. We can start looking at how we can get doctors involved and like streamline that process, and both can happen simultaneously.
How many sets of slides will you need?
So, to start with, we put up how do I go there? The request for the data set. So as you mentioned correctly, in the classification setup, we will just have to name the slide itself as does it have cancer or not. And then we can have it in the lowest resolution that you have, medium resolution that you have, and the highest resolution you have. So we can kind of see the difference in how correctly we can identify cancer in all of those levels to experiment with. And sorry, this is the slide I want you to see. And then if it's for breast cancer metastasizing in the lymph node, because we already have this data set that is very rich, we can start with as little as 35 to 50 slides that are labeled as cancer or non-cancerous and go from there. So to start with, we can start with maybe 5 or 10. And if everything looks fine, we can go and do the 50. And then we can see how we perform on that test set.
Yeah, so basically, if you get the images from just uploaded to a Google Drive or a Dropbox, that should work, right, to start with?
The first iteration, but see, those are the things that we don't want to be. So we ideally want to get to a system where we have taken care of the streamlined process. So once we have the infrastructure, we have some scripts that either helps Abhijit or the doctors to upload, and then we will access the same things. And these structures, if we have a format, this entire process has to be just done once, and we can repeat the same thing n number of times. So next time around, when we go to x-rays or whatever, we don't have to worry about the logistics of those things. It doesn't have, if someone is manually packaging everything and manually doing all of those things, it's also time taken away from their day. So my inclination is to that's why I have the structure also mentioned here. So like once we have this and it works for the first time, it'll take a little bit more time, but then we can write scripts to automate them. Like Fran and I can do it as well for you guys. And then all they'll have to do is just like run some scripts, and then you can upload it to the right places, and we can pick them up from the right places. So we can just let the computers do that for us. All of us are accessing it through the internet, and the database lives on the cloud, and the virtual machine lives on the cloud. So ideally, the location, the physical location of the database itself will live within India. I think that is the privacy law that we talked about, and that's what we want to do as well. So what, like the example that I mentioned now about datasets being streamlined is when Abhijit and the doctors upload the dataset, all you'll have to do is, once we have the setup, run a script that will upload all the datasets that you collect and have labeled and everything up to the database. And then Fran and I will write some scripts that will be living on this machine that will just look at the database itself. So locally, we will not be taking any of your data down to our computers, and like it will never leave the cloud infrastructure that we have signed up for. So privacy wise, that's one of our first concerns and like our top priorities. We do not want to kind of put the data set or the people's information at any kind of risk. And this is kind of what we do at work as well. So we just follow the same standards, and hopefully that works for you guys. And the next thing is, this is the technical pipeline. So once we have a data set and an image, typically, maybe I'll just present the slide so you can see it better. So once we have a data set, we will have to run some preparation on it. So that basically means cleaning up the images. So once you have the slides, we'll probably do some uniform operations on them to bring them to a condition that makes it best for the system. And then we will do some kind of feature extraction that like augments or rotates the images, because we don't want it to learn a specific thing that's how to say, it's like if all your image photos are taken in one kind of corner of a room or low light conditions, and then your test cases are in bright light conditions, we want to kind of anticipate that and like take that into account. So we will do all those kinds of operations beforehand as well. So there's going to be some kind of standard operations that we would do. This is standard no matter what task we're doing. It's typically followed for most kinds of image tasks. And then we'll have the model training itself. So going through the different examples and training the parameters for the model. Once that is ready, we will be testing it on some test data. So when we train it, we will hold out a particular, let's say you have 100 images, we will take out maybe 20 of them, and then we'll train it on the 80. We won't show it the remaining 20. And during test time, we will test how it does on the 20 to kind of mimic what will happen in real life. Because if you give it all the examples, you can kind of memorize it, and then you might get 100 and 100, but you want to give it some kind of variability, right? So that's what will happen here, and we'll do that a few number of times to get the best model out. Once we have that, we'll take the model and then we'll test it in real life with like predictions and whatnot, and we'll see how it's doing. And we'll probably iterate this process a few times before we can get to the right model for the task that we're looking at. This is the standard machine learning pipeline. Yeah. And yeah, that's all we had. Thank you so much for your patience.